Thank you. Thanks for having me. So I believe many of you, well, perhaps all, understand what Pauli stabilizer code is. Anybody heard of that name first? I guess not. Oh. Well, okay, so a lot of people just call it stabilizer code. I tend to call it Pauli stabilizer code because stabilizer has been the word for many other things. So more specific, Pauli stabilizer code. What is it? We get a some commuting set of operators in the group of all Pauli matrices, and then we have a group that does not contain identity, and we define the subspace of all vectors such that the vector is stabilized by every element in the stabilizer group, and that's our code space. And we know that how do you make use of this by applying certain gates and so on. In this setting, perhaps, well, by now this is perhaps a textbook material. It is textbook material. Once you define this, the next thing you will define is what the logical operators are, which is the commutant of this group, or in the more group, there's the language centralizer of the stabilizer within this Pauli group. And when it comes to error detection and error correction, then you will learn that, okay, some error is happening. How do you model that? We think of originally a code state is now mapped by some error and becomes the error applied operator. And by measuring the eigenvalue of this H stabilizer on the error contaminated state, we wonder what will come out, what the eigenvalue, this value, would be. And that's, depending on the sign, we detect errors. And based on that information, we correct errors. And once we find the correction that this all information turns out to be a +1, then we say that the error correction is implemented. And we wonder about whether that was successful or not. How do you test it? Anyone answer? It's all textbook material. How do you test it? If the residual error, the error plus the correction, well, error times the correction operator ends up outside this stabilizer group, then we say non-trivial error has occurred, and we say that that's an uncorrectable error. Any question for this? It's all standard. Now, I want to say exactly the parallel things for the Floquet codes. There has been a lot of activities for this question, and I hope that our work is probably the simplest of all. So let's start with the definition. Oh. So what is a dynamical code? In a sense, dynamical code is simpler to define. Why? Because I don't get to talk about the subspace anymore. I only get to talk about the definition of dynamics. All the rest is now tossed to yourself how to analyze that. So I start with empty. Say, well, what's a canonical state that you can pick? Well, I would choose maximum mixed state because there's no base. It's basis independent. And the proper stabilizer group to describe that empty maximally mixed state would be just a trivial group of identity matrix. And then I make some measurement. Okay? And then I make another measurement. And I keep doing. That's it. There's no subspace. There's no commutativity requirements. Nothing. It's just a sequence of measurements that are defined beforehand. That's my dynamical code. Oh, well, for the sake of this talk, I make exactly one measurement at a time. Let's make it simple as possible. Identity, the trivial stabilizer group. and I make a measurement, Pauli 1, Pauli 2, and dot, dot, dot. There's no restriction on the weight or anything. That's the job of engineer at the moment. I could be an engineer, but let me be a mathematician at the moment. So that's my dynamical code. And the Floquet code, yeah. So that's my dynamics. Floquet code is when this.
You do a measurement, you restrict on some outcome, or do you not?
No, nothing. Literally, my entire prescription for my dynamical code is that, oh, yeah, here's a sequence of Pauli operators that you have to measure. Period. And the Floquet code is nothing but there is a periodicity. After some number of measurements, you repeat your measurement. In the instruction set, it is not guaranteed that you will have the same outcome, but it's just that if you measure the sigma xx here, then you will have to measure sigma xx there again. That's it. So Floquet code is nothing but that. Okay. How can we understand whether it is encoding anything? Okay, so to understand that, let's think about the so-called instantaneous stabilizer group. I started with the trivial group, and if I make a measurement, then my whole state is collapsed onto the eigenstate of this Pauli operator. So at this moment, I will have a rank 1 stabilizer group that depends on the measurement outcome of the measurement operator. But this is my stabilizer group. If I make a second measurement, this measurement will alter this. And now it becomes important whether they had a commuted relation or not. So let me just briefly review what's going on when you measure some Pauli operator on top of a stabilizer group. If you had a stabilizer generators, and if you are bringing another Pauli operator that you have to measure, then what happens? There are two cases. First one is M is already in this stabilizer group. Then what happens? Then you're basically measuring an operator whose eigenvalue is known, so you should reveal that eigen operator, and this stabilizer group does not change after the measurement. If it is not a member of the previous stabilizer group, then there are two possibilities. Still, M could be commuting with everything in your stabilizer group or not. If it commutes with everything, then think about a situation where you have projected some number of qubits into the +1, say, spin-up states, and then you get to measure another one along the same basis. Then you are projecting that unknown state along the direction, so the number of stabilizers will increase by 1. And if there exists an element of the ISG such that it anti-commutes with the measuring operator, then effectively you are kicking out that operator, and the remainder you keep it. And M just replaces the position of what is kicked out. And the rank of the instantaneous stabilizer group stays the same. It's like you prepare the qubit along the z-axis, and then you go ahead and measure along x-axis. And the z stabilizer will drop out. Your qubit will be projected along the x direction, and now your new stabilizer group has the same rank. So this is all you need for the dynamics to keep track of what's going on. Key point, the rank of the stabilizer group never decreases. Either it stays the same, revealing the eigenvalue, it stays the same by changing the stabilizer group, or it increases by inserting one more operator. So given a measurement dynamics, if I keep track of the instantaneous stabilizer group at every moment, it should be a monotonically non-decreasing function, yes?
So I guess you're saying that you can always find the dynamics at the always exactly one data type that you're
everything must be said in terms of linear algebra. So if there exists a one thing that is anti-commuting, then you can rearrange your basis in just such a way that exactly one basis element is anti-commuting and all the rest is commuting. So rank will be sometimes stays the same, sometimes jumps up by +1, sometimes stays the same, +1, and go on. And my dynamical code, or a more general class than the Floquet code, will encode a logical qubit if this asymptotic value is not the maximum possible. If it hits the rank n, then you are immediately in the pure state. If it's smaller than that, then there is some elements left in this originally entirely completely mixed state. Now you are left with some subspace at that instant moment. Of course, it doesn't mean that the subspace is static there. It keeps changing, but nonetheless, the rank is the same. So there is some fixed dimension worth of space that is left, and it's moving around. So that's how you figure out how many number of encoded qubits there are in your dynamical code. Okay. Now let's talk about detectability. When do you know there has been an error? By only looking at the measurement outcomes. Okay, let's come back here. Because we make exactly one measurement at a time, this is sufficient to look at exactly, the situation. In this case, when you are measuring an element that is already in the instantaneous stabilizer group, you know what you will see. And any deviation from that fact is an indicator of that something wrong happened. Aha. So that's the detecting event. Any other case, what is the measurement outcome in this case? It is, in the strongest sense, random. Why? Because that means if my state was psi, and which was stabilized by some s, say that's the situation, and s happens to be the anti-commuting operator to my measurement outcome, then my measurement probability of getting +1 for measuring m would be this. But plugging this equation, just a direct consequence. But since they're anti-commuting, I would pick up minus there. And that is the probability of getting minus outcome. And I started with the probability of getting plus outcome. So they have to be 50-50 random. So in this Pauli measurement setting, the measurement result is either deterministic, and the value you can infer from the previous outcomes, or it's a coin flip. And from coin flip, there's no information. So any detecting event must be all formed like this. There's no other choice. Okay, that's the detection of error in the Floquet code. Now, we want to say, what does it mean? What does it mean to be non-trivial in this case? Okay, well, to understand what's non-trivial, I want to understand what's trivial. And to that purpose, I want to look at the action of errors. So what's the dynamics? Well, there are many possible ways to characterize this, but for me, for this to understand this, I think of the evolution of density matrices. So at every instance, I record my density matrix in my head. But there are cases where measurement outcomes are random. How can I capture that? Well, simply we can use the formalism of mixed states. So let me define the measurement channel. Sorry for the same symbol, but it means the same thing, so let me use the same symbol. The measurement channel applies the measurement operator. This is the projected measurement, post-measurement state upon the plus outcome. And I record my outcome in some other register. And I can also do the minus outcome case. Oh, yeah. And record the outcome. And if I keep track of such density matrices, then I don't have to worry about whether the measurement outcome is random or deterministic. You know, this formula will take care of that automatically. So in this result recorded sense, my sequence of density matrices knows everything about my dynamics. Okay. Now let me make another continue the analogy. In the usual Pauli stabilizer code, the error acted on the code state. It was a state. And in this dynamical setting, we need to talk about the error that does come with time coordinates. At every time step, there could be some error, which we model as a Pauli operator that is inserted at every time step if possible. And such an error, space-time error, will be acting on the set of chains of density matrices. How? Originally, in the pristine evolution, we had this. But with the effect of errors, it becomes it derives a new sequence of density matrices contaminated by the error insertions every time. And this formula captures exactly the action. So now by inspection, well, you can do a little of the writing, but almost by inspection, that the group of all space-time errors have a group action on the set of all chain of density matrices. Okay, that's how errors act on the state. Not only a single state at a certain time, but on the history. That's how errors act. Yes?
With your density problem, should I think of it as the dimension of rows increasing?
Yes.
Okay,
Yep.
so you've got some extra register that encodes the measurement history.
Yep. Okay, that's how errors act. Now, detection event. So now, well, David brought the good point. The measurement register is increasing as the time goes on, and by looking at the measurement outcomes only, I can tell whether a certain deterministic measurement went wrong or not. That's all we got. So we should be able to tell whether something went off or not. So as long as the measurement results make sense, I cannot tell whether there was an error or not. So that's my undetectability. You look at the action from the error on the set of chain of history, and then you look at the measurement outcome register to tell whether there was an error or not. And more important thing in this dynamical fashion is that we always think about asymptotics. Does the state eventually becomes equal to the intended state? Then our lives is good. You know, something crazy might happen intermediately, but as long as that effect goes away, we'll be fine. That is acceptable, yes.
So are you restricting to having at most one error?
Since it is a group action, that's not a problem. I mean, that's up to your design.
Yeah, but the concern is that any error could be detectable, but there could be two instances of errors that you cannot distinguish.
That's precisely the meaning of triviality. I'm coming to that. Now that you are thinking about the dynamic code in this fashion, it is legitimate to talk about harmless errors. Okay, let's come up with some candidates. What can be harmless? Okay, I projected down to the eigenspace of M at that moment. If I act that instantaneous state by the very measurement operator that I just measured, it will certainly be harmless. It's exactly the applying a Pauli stabilizer state by a stabilizer. So that's number one. And we actually give a name. We call it vacuous error. It's a one time step supported space-time error that is exactly the operator that you are measuring at that moment. Certainly it does nothing to the history of the density matrices. Number two, if I do something here, do something here at the previous time step, and if this P commuted with my measurement operator, and I apply the same operator once again after the measurement, then what happens? Nothing. Right? Well, I mean, it's trivial. You did something, measurement didn't see, I cancel that. Nothing happened. By the way, this does not mean that the history of the density matrices is invariant. This actually changes. At the very moment I apply P, then P times rho T may be out of my intended sequence of density matrices. But then immediately it got corrected by the next step. So at some point, we call this sandwiching error. At some point in the measurement history, sandwich error may change, and then it does change the history, but eventually it doesn't. Makes sense? Yeah.
Do you find a sandwich error or a single time step, or do you count after?
Single time step. Yeah. So formally, yeah, vacuous error is the exact error that matches the measurement operator. Sandwich error is a pair of errors supported on the consecutive time steps such that it commutes with every measurement in between. Clear? And the main theorem is that that's all. Yeah, well, not technically, but you can. Yeah, I mean, you just conjugate the measurement by the anti-commuting Pauli operator. That's it. So, is the statement clear?
What if you have sandwich error, but like multiple measurements?
I'll get to this, yes. But at the moment, is there any ambiguity or confusion at the statement?
Vacuous error is just that measurement exactly.
Yeah.
Not the statement.
No.
So if I have a particle,
Yep.
and I have an E particle, and I have like an E boundary,
Mm-hmm.
an E particle appears,
Mm-hmm.
will be detected,
Mm-hmm.
then it just remains near the boundary, will completely detect it, and then when you act it for the same boundary,
Mm-hmm.
it's detectable, because it's detectable.
Yeah, that's detectable.
But what if it does it very fast? Like, or in some, if there's
That's exactly what happens in the Vios example, which we will see later.
You say here it exists the sequence of measurement such that that's true? Or are you saying any sequence of measurement, this is true?
For any sequence of measurements. One important ingredient. In the steady stage, I draw the rank becomes like this here. So any space-time error inserted in that steady stage, if it is undetectable and correctable, then it is a combination of these obviously harmless, benign errors.
So we should take it as a no-go theorem in a sense that other than these trivial cases, all undetectable errors are not correctable?
Right.
So it's just sad news.
Yeah. Well, I mean, I'm just giving you an explicit set of trivial errors, quote unquote trivial, in complete analogy with the Pauli stabilizer static codes. In the static codes, undetectable errors comes in exactly two classes, one trivial, the other non-trivial. Trivial class, it consists of stabilizers. Non-trivial classes, that sits outside the stabilizer group. I'm giving you that kind of dichotomy. If it is undetectable, correctable in a steady state of my Floquet code, then it is always a combination of this. Otherwise, it is undetectable and logical corrupting error. And no decoder will ever be able to correct it. Okay. So let's think about why this is the case. Here, now it comes very handy to understand this in terms of history of density matrices. I want to reproduce my whatever undetectable error that happened in the past. I want to reproduce the action of that now. What does that mean? Well, think about the Pauli stabilizer codes. Some error has happened on some part of your code space, and it has implemented a logical operator. And I'm sitting somewhere else that the logical error did not touch anything. But then, by multiplying some stabilizers, I will be able to reproduce the action. In other words, I will be able to find the representative of the same logical class, same logical operator class, sitting here. I want similar thing here, but in the time direction. Space-time error has happened in the past and is assumed to be undetectable. Then I claim that you can always reproduce the same action, eventual same action, by the current time step. On top of that, I will argue that if you go a little bit further into the future, then that equivalent realization is actually a logical operator, trivial or not, at the instantaneous stabilizer group. Then this makes sense. You started with the undetectable error. I found the equivalent action at this very moment. And if it turns out to be a stabilizer at that moment, that's certainly correctable. You don't have to do anything. There's no eventual action to the history of the states. If it's not a stabilizer, then there's no way your logical qubit failed. Okay, so I have to show two things. That I can always realize the undetectable errors action at some future moment. Second, that action becomes a logical operator. Okay, first thing. Yeah.
That kind of operation, is your theorem valid?
In some sense, yes. Can we defer that question a little bit later? In some sense, yes. Not in an absolute sense, but in some reasonable sense, yes. Okay. So let the time go to the right. So I have all the instance of my code dynamics. And some error, say, these two time steps have happened. So this time step t and t plus 1. T is the first time step where the error component appears, and t plus 1 is the later one. Now, there will be some measurement at this moment, and the error has occurred at this location. Okay, let's think about a situation where m is a deterministic measurement. Now, I told you that there are exactly two cases. Either it's a completely deterministic or completely random. If it is deterministic, then that's a detection event. So if ET did not commute with M, this measurement will know it. By the undetectability assumption, they must commute. But think about the sandwiching error. Sandwiching error allows me to cancel this and move this error component to the next time step. So if I insert this sandwiching error that has eventual no change in the history of density matrices, I will cancel this effect, cancel this error. You know, remember that the action from the group of errors is a group action. So I will cancel this and left with this. So effectively, I have moved the position of my error to the next time step. Now, that was the assumption, that was under the assumption that MT was a deterministic measurement. Now, if it is not deterministic, then we have to worry. Well, if it's not deterministic, there are two cases. It may be commuting, in which case we can still apply this sandwiching error. If M was undeterministic and ET was not commuting, then how can it be a random measurement in the steady state? It must be because the instantaneous stabilizer group contained an element that anti-commuted with M. And I can dress this E with that stabilizer and make it commute so I can push. Another kind of fact, small fact, is that every stabilizer is a combination of those. Why? Because you have built your instantaneous stabilizer group using those operations. Where does the new element in your ISG appears? It's because of the new measurement. You sometimes kick it out, but nonetheless, every element is a product of some previous measurements that is propagated through these sandwiching errors. So those benign errors always contain instantaneous stabilizers. So I'm free to modify my E by any stabilizer by multiplying certain benign errors. So in every case, I can find the equivalent error in the sense of the eventual sameness of the history of the density matrices, so that I can cancel the action at the moment, the very first moment. And if you've done the first thing, then the rest is by induction. You can push it indefinitely towards the future. Okay, so
What are you pushing? Like once you address that, like when you say push, what do you mean?
I am removing the time component of an error such that the resulting transformation implements the exactly same action eventually. I'm emphasizing the word eventually. It does not leave the state invariant. The whole history is changing. Eventually it's not changing. So I managed to push the errors all the way however far into the future I want. Now, second, how does it become a logical operator? That's a non-trivial property, and I cannot guarantee in the full generality. And that's where the property we call bounded inference comes in. Okay, let's focus on the Floquet code. Floquet code by definition is periodic, right? Now, if you reach this steady stage, then every stabilizer group is somehow inferred from the past. And fix your some stabilizer at the moment that is inferred from the past. And there is what do I mean by inferred from the past? There is some sequence of measurements whose product results in this stabilizer. I just copy that and then pull it over to here to the present. Then the conclusion is instantaneous stabilizer element at that moment is a product of the measurement outcomes in this window, not far in the past, but this window, bounded inference. Now, that means every stabilizer is inferred from some small window, and I can think about the state far into the future, where certainly my measurement outcomes are not affected by the errors at those moments. Then conclusion is, at this moment, error is far that way. At this moment, every stabilizer is inferred from the measurement outcomes, and the whole code state must be consistent with the measurement outcomes. In other words, this state is in the code space of the instantaneous stabilizer inferred from the measurements. So I am in the code space, always. And I told you that you could always push your errors far into the future. And let me bring it to the position where I know that I am in the code space. Okay? I always remain in the code space. Error has occurred. How can that be possible? And I know that error is acting on that very moment only. That's possible if and only if the error is a logical operator. Yeah.
Can you maybe give an example of something that is not bounded inference?
You can cook up by breaking of course you have to break the periodicity. You can cook up. Yeah. You can also study how large this window you should take. And the one trivial upper bound is that this initialization time until you reach the steady stage and 1 period. And that's enough to infer all your stabilizers from the past. Yeah.
Okay, so is something with bounded inference just thinking about like the chain of independent qubits, just like I measure z on one site the first time, and the rest I do some different Floquet on all the other qubits.
Yeah.
It's not bounded inference.
Well, that's not going to be a boundary inference, right? Yeah, yeah, yeah.
Can you just say the definition of boundary inference again?
If your stabilizer group, it can be inferred from the measurement outcomes in the time window of size that is constant. Constant independent of the time, the clock, the time, coordinate.
But it can depend on like system size.
Yeah, yeah. Actually, it must. We have an example where the initialization time is actually proportional to the number of qubits, even though the period is like 4. Okay, so let's see the theorem in action. Can I? Yeah.
You confused what kind of error are you considering? You said the error never take you out of the code space, but if I imagine a very simple situation, taking a protocol with repeated measures, single repeated. You're saying this error is never detected by any.
Well, I mean, general errors will generally be detected, and that will kick you out of the designed sequence of density matrices in history. But if you assume that it is undetectable, then we wonder what happened, what's going on. Yeah. Yeah. So, I just want the screen. So the example I will show you is example by Villon, Christopher. Yeah, by the way, this is joint work with my student Keller Blackwell. So Villon considered a variant of a honeycomb code with a boundary. And just to remind you, the honeycomb code was defined on a trivalent graph using 2 qubit measurements, and you color them in 3 colors and you assign the measurement operators according to their color. And you do the measurements in a period of 3 sequence, and that encodes some number of qubits depending on the topology. This version does the same thing on this honeycomb lattice with the qubits on the vertices, but with the spatial boundaries. The spatial boundary is a hexagon. And he literally took the period of 3 thing and then just declared that, oh, this is the code. If you examine the instantaneous stabilizer groups, Actually, this example has a very short initialization time, like 3 or 4. I forget the exact number. But and every instant, it is isomorphic to the surface code. And so if you make it big, then every instance you have a large code distance. Does it have a large Floquet code distance? Oh, by the way, it's behind the board. But since we have the dichotomy of the undetectable errors, we can now declare that, oh, the code distance of a Floquet code is the minimal weight of undetected errors that is not benign. As clear as it gets. And then according to that Floquet code definition, this has code distance small. How small? At most 2, actually. So let me tell you why that is the case. So this is the answer. Well, but before you look at and read the text, if you're given a space-time code, like a dynamical code or Floquet code, given an error configuration, maybe it's a nightmare to figure out all the detecting events and the commutation relation in space-time to figure out whether this error is truly undetectable or not. It can be a very non-trivial calculation. I mean, if you try it, you'll realize soon. But using these benign errors, if you could manage to transform a given error configuration into a logical operator using benign errors, then you're guaranteed that the underlying error that you started with is undetectable. You don't have to calculate your detectors. Benign errors are detector preserving transformations, and therefore, if it is ever undetectable at some point, then it's all undetectable. Okay, so what's the weight 2 error that causes logical failure? We start with the corner. Oh, okay, so the dynamics goes like this. At time equals 0, all the x checks, the red edges are measured, x-axis is measured. Time equals 1, the blue edges are measured by the ZZ. Time equals 2, the YYs are measured along the green edges, and you go to the period. You start with the x over there. You just measure the xx checks, and you insert the extra x error at that corner. Then, using vacuous errors, the measurement operators at that moment, you can deform that x operator into the weight 4 operator like that. It was completely benign, but why did we do that? That's because we want that the error to be commuting with all the subsequent measurement, the ZZ checks. If you do it, then it becomes commuting with the ZZ checks. And you again decorate at that moment using another round of vacuous errors to insert the ZZ checks and change the XX into YYs. And that representation commits with the next round of measurement. So you end up with the weight 4Y fully supported on the time slice of coordinate 2. Then at that moment, you insert another Y. So overall, except for those benign errors, all I did was inserting the X at that corner at time equals 0, and another Y error at the time equals 2, weight 2. But now you have a logical operator along that boundary by the combination of the inserted errors and some benign errors. And that's a logical operator. So Buyon's example, even though the instantaneous stabilizer group had code distance large, you end up with the code distance at most 2. Quite dramatic difference between the minimum overall code distance of ISGs versus the Floquet distance that we just defined. Okay, my time's up. Thank you.
One or two quick questions.
If you give up this bounded inference assumption, is it just that the proof doesn't work, or the statement becomes untrue?
It's tricky because of, well, it's all because of the potential benign errors that could be generated by those in the future. And I don't know how to do that. Well, I mean, the hard step is to show that undetectable errors ends up in the logical operator at some point. It may stay as some exciting error at the very moment, but the bounded inference property ensures that after a certain number of steps, you are coming back to the code space.
But you don't know that it definitely fails if you give up that assumption.
Right. Well, I guess it fails. Yeah. Oh, by the way, you don't need the constant inference window actually. All the conclusion can be shown as long as you can eventually become on the logical space, which means if the inference window size is less than the full time history, then you're fine.
Is this weight to logical arrow an example that only exists in the Floquet code on open boundary, or does it also exist if you have put it on a torus?
Put it in the torus, this doesn't happen. Well, you may wonder how come we and people have declared the fault tolerance of a Floquet code without this criteria. Well, for the examples that are written in the literature, all the analysis happen to have a decoding graph. So you analyze the detecting events on all the usual syndrome map, and you realize that it realizes exactly 2 syndrome bits. I mean, yeah, there exists a basis of space-time error such that every elementary error excites exactly 2, and you build up the decoding graph, and you show that every small loops have no consequence, although it didn't have benign errors back then, but anyway, you can show that it is harmless, and based on that, you build up your fault tolerance. Yeah, this example appeared precisely that work and this work, somewhere between. And this is just an example.
Thank you.
Let's thank Jeongwan again.